Let us embark together on a wondrous journey through distant stars and the profound secrets of the cosmos, where everything we once thought familiar suddenly transforms into something mysterious and deeply inspiring. Today, I invite you to sit back, close your eyes for a moment, and imagine you are floating in the vast expanse of space, where enormous galaxies swirl in majestic silence, accompanied only by the gentle whisper of cosmic winds, a sound not heard by human ears, but felt as the heartbeat of your own soul when confronting the infinite. We will explore dark matter, a hidden force cradling our entire universe, and in future stories, we will glide through dark energy, its enigmatic companion. But let us begin with dark matter, for it is like a quiet friend, always present to prevent everything from descending into chaos, stirring in us a sense of awe mixed with a slight shiver before its invisible power. What exactly is dark matter, my friend? Picture it as a veil draped over everything, a silent yet immensely powerful form of existence, not something we can touch or see with ordinary eyes. If we believe, and indeed, the vast majority of scientists worldwide hope and trust that it exists, then dark matter is an invisible type of matter permeating every corner of the immense universe. This is why it is called dark, not because it carries a gloomy black hue, but because it evades light, dodging all our attempts to illuminate it. Scientists, those passionate individuals obsessed with grand questions, have spent centuries unraveling the structure of matter, tracing the origins of the world around us. Think of this journey as a long adventure, starting with ancient Greek philosophers and their atomic theory, envisioning tiny indivisible particles like small pebbles tumbling in the cosmic river. Then came the ancient Chinese five elements theory, where metal, wood, water, fire, and earth blend into a harmonious symphony, explaining the balance of all things through natural elements rich in color and emotion: radiant fire, gently flowing water, steadfast earth embracing all. From there, humanity has constructed magnificent models: the planetary model with perfectly circular orbits, the electron cloud model where tiny particles dance around the nucleus like performers at an endless ball, and the modern quark model in particle physics, with minuscule pieces forming protons and neutrons, carrying the might of the strong nuclear force. We also have the periodic table of elements crafted by the Russian chemist Dmitry Mendeleev. I always picture him as an elderly man with sparkling eyes, sitting at a worn wooden table under flickering candlelight, arranging paper cards with childlike delight, and the standard model of particle physics table, where everything is neatly categorized like a vast library. We proudly believed we had a solid grasp on the levels of matter in the universe, from familiar atoms to mysterious subatomic particles. But then, like a gentle yet profound shock, the latest astronomical observations forced us all to pause, take a deep breath, and wonder, how much do we truly know? After years of tireless research, with long nights beside frigid telescopes, physicists uncovered a truth that quickens the heart. Everything we have studied, classified, and cherished accounts for less than 5% of the universe's composition. Imagine brewing a cup of coffee, thinking the entire cup consists only of the visible grounds, but in reality, 95% is something invisible, odorless, colorless, filling the space and determining the true flavor. That is dark matter and dark energy, things we cannot see or touch with any senses. They do not interact with light waves or electromagnetic waves like the ordinary matter we know so well. Ordinary matter, no matter where it hides in the universe, reveals itself the moment a ray of light shines upon it. Even when ordinary light is too faint for human eyes, we cleverly employ ultraviolet rays sparkling like daytime stars, infrared warmth like autumn's breath, sharp X-rays like exploratory blades, powerful gamma rays like distant thunder, and whispering radio waves, all to uncover hidden secrets. But with dark matter and dark energy, all those efforts seem to vanish into nothingness. They react to nothing, like silent phantoms gliding through layers of light without leaving a trace. So if we cannot see dark matter and dark energy, how do we know they truly exist? Listen to the whisper of gravity, that invisible thread connecting everything in the universe, drawing us closer in a warm yet authoritative embrace. They may escape the pursuit of light waves, but they cannot evade gravity's binding. That is the key, the way humanity, with perseverance and extraordinary imagination, has detected dark matter through clever indirect methods. Although the true nature of gravity remains a thrilling mystery like an unfinished poem, always inviting us to read on, the theory of it is tied to two great scientists who forever changed how we view the world. First, Isaac Newton, the Englishman with long hair flowing in the damp London winds, sitting under an apple tree in his peaceful garden on a summer afternoon in 1680, when a falling apple sparked his law of universal gravitation. He penned elegant mathematical formulas explaining that every object in the universe pulls on every other with a force inversely proportional to the square of the distance, making us feel a profound connection between Earth and distant stars. Then came Albert Einstein, the German physicist with deep, thoughtful eyes, who elevated us to new heights with general relativity. Picture him in a small room in Berlin, surrounded by pipe smoke curling around pages dense with formulas, on the 25th of October, 1915, when he presented his paper The Field Equations of Gravitation at the Prussian Academy of Sciences. That was a historic moment, when he joyfully announced to the world the birth of general relativity, a theory not just mathematics but a poem about the cosmos. Its core idea can be summarized in the famous words of physicist John Wheeler, whom I envision as an elderly man with a mischievous smile by a warm fireplace. Matter tells spacetime how to curve, and spacetime tells matter how to move. Let those words sink deep into your heart, because matter exists, spacetime bends like a soft fabric under the weight of stars, and that curvature guides matter's motion, creating enchanting cosmic dances. This differs starkly from Newton's gravity, where the force is like a direct pulling string. Here, it is the warping of space and time itself, an abstract painting making us feel small yet connected to everything. For example, consider small celestial bodies orbiting near our Sun, our planet, and its stellar siblings. According to Newton, they are pulled by the Sun's gravity, a simple yet powerful tug, like an invisible father's hand embracing his child. But Einstein's general relativity is more poetic. The Sun's enormous mass curves spacetime around it, creating a winding path, and the small bodies simply slide along that curved orbit, like leaves falling along a meandering river of time. This spacetime curvature is truly evident on grand scales, where massive bodies and galaxy motions paint vivid cosmic pictures, causing scientists to exclaim in discovery's joy. In recent years, thanks to technological advances, giant telescopes atop towering mountains where winds howl through icy crevices, and satellites orbiting Earth with the soft hum of engines along with refined observation methods, fields closely tied to general relativity have flourished. We speak of the Big Bang Theory, where the universe exploded from a scorching point 13.88 billion years ago, a silent blast echoing through all voids, black hole physics, those light-swallowing pits where time slows, and the universe's expansion, where galaxies drift apart like old friends parting in the night. These achievements not only solidify general relativity, making it sturdy like an ancient mountain, but also pose fresh questions, exciting challenges to existing physics theories, keeping scientists awake with cold coffee and dancing equations on computer screens. And dark matter, alongside dark energy, is one of those grand mysteries, a puzzle evoking excitement and humility before creation's vastness. As early as 1932, Dutch astronomer Jan Oort, after whom the parsec unit of astronomical distance is named, representing light's journey over 3 years, proposed dark matter with fierce conviction, based on meticulous observations of star motions in the Milky Way. His greatest feat was calculating the Milky Way's rotation formula by hand, a complex task like weaving a tapestry from invisible threads, revealing something holding stars from flying apart. Around the same time, Swiss astronomer Fritz Zwicky, with an adventurous spirit and eagle-sharp eyes, inferred dark matter's existence through studies of galaxy clusters, those colossal companion groups floating in space. In 1933, both proposed dark matter, and the latest observational data are touching confirmations, like discovering a dusty old letter in a drawer. There are two strongest pieces of evidence for dark matter's existence, two stories that make us ponder: galaxy rotation curves and gravitational lensing. The galaxy rotation problem was first discovered and studied by American astronomer Vera Rubin, a woman with a warm smile and steel resolve, who spent long nights at the Kitt Peak National Observatory telescope, where Arizona's desert whispers under moonlight, examining galaxy rotation speed curves. She found that stars far from galaxy centers move much faster than theory predicted. They do not slow like tired runners at a race's end, but speed on with undying power. The faster the stars, the more enormous the gravity needed to hold them, like a tighter embrace to keep a loved one close. Where does this extra gravity come from? It is assumed to originate from dark matter, the invisible veil cradling the galaxy, creating inspiring balance. When studying our own Milky Way, a cosmic home shaped like a flat disk, spinning in grand silence, astronomers found a large amount of dark matter in its outer regions, where light fades into darkness. Physical observations show the Milky Way has a diameter of about 100,000 light-years, a distance overwhelming when considering sunlight takes 100,000 years to cross it. According to gravity theory, stars near the center should move faster than those at the edges, like children playing closer to a playground center. Yet astronomical observations paint a different picture. Stars both inside and at the edges orbit the Milky Way's center at nearly the same speed, a steady and harmonious waltz, evoking the universe's miraculous balance. This indicates a vast amount of dark matter in the Milky Way's outskirts, forming a gigantic dark halo with a radius about 10 times the visible regions, roughly 1 million light-years, a sphere of darkness embracing light, like a mother shielding her child in the deep night. Dark matter's gravity fits perfectly with general relativity, as it can curve spacetime, subtly warping the cosmic fabric. When light passes through this curved spacetime, it bends, similar to light refraction through a lens in an old microscope, where shimmering water droplets distort images but reveal hidden details. Based on this principle, Einstein proposed gravitational lensing, and some call it Einstein's telescope, a gift from nature he predicted with childlike joy. Fritz Zwicky in 1937 pointed out that galaxy clusters containing dark matter could be ideal for creating gravitational lensing effects, where dark matter's relatively uniform distribution produces higher quality lenses than those from dense objects, like pure crystal glass compared to rough ordinary glass. However, it was not until 1979 that gravitational lensing was confirmed through dramatic astronomical observations, when scientists cheered in dim control rooms as screens flashed with distorted images of distant galaxies. This shows dark matter does not interact directly with light, it neither absorbs nor emits rays, which is why we cannot see it with naked eyes or telescopes. But dark matter can indirectly affect light's propagation through gravity, bending ray paths and serving as a medium for gravitational lensing, a poetic way the universe reveals itself. As we know, the invention of the telescope was immensely significant for astronomy, since human eyes can only observe within very limited ranges, like a flickering candle in a storm. But who would have thought nature had already created numerous giant telescopes suspended in the night sky, awaiting human discovery and use? Those are Einstein's telescopes we mentioned, invisible masterpieces sparkling among stars. So what role do these telescopes play in our journey? Astronomers use them to observe distant galaxies, those faint light islands at the universe's horizon, where light travels billions of years to reach us. Observing distant galaxies aids in studying the universe's evolution and formation, evoking a sense of time travel, listening to the past's whispers. Because light from these galaxies was emitted billions of years ago, in a sense, viewing distant galaxies is viewing the universe's past, like an old film slowly replaying creation's early moments. For instance, according to the Big Bang model, the universe began 13.88 billion years ago, a massive explosion from scorching nothingness, releasing energy and time into existence. Thus, observing an object 10 billion light-years away means seeing it as it was 10 billion years ago, when the universe was only 3.8 billion years old, a youthful era where the first stars flickered like hopeful flames in primordial darkness. This is one of gravitational lensing's wondrous effects, allowing us to touch cosmic history with profound emotion. And the exploration of dark matter does not end with old tales, it continues with fresh advances, making us feel the universe whispers new secrets daily. Just a few days ago, in November 2025, scientists announced an intriguing study on how dark matter might be returning in the mystery of gamma-ray glow from the galactic center, an enigmatic shine many believe could be traces of dark matter particles colliding and decaying. Imagine those gamma rays as tiny fire sparks in the night, suggesting dark matter not only exists but interacts in ways we never dreamed. Simultaneously, researchers are exploring the idea that dark matter may hide in a fifth spatial dimension, where fermion particles, basic building blocks of ordinary matter, could travel through invisible portals, explaining why we do not see them in our familiar dimensions. This stirs a sense of adventure, like opening a door to parallel worlds where dark matter dances freely, unbound by our three-dimensional rules. Furthermore, dwarf galaxies, humble smaller siblings of giant galaxies, are becoming key to resolving heated debates on dark matter's nature, with new observations showing they may harbor higher dark matter densities, helping paint a clearer picture of this invisible veil. Picture those dwarf galaxies as small coastal villages in the cosmic sea, where grand secrets hide in simplicity. Earth-based experiments are also tightening the net around dark matter. For example, physicists are using lead from ancient Roman shipwrecks, salvaged from Sardinia's seabed 2,000 years ago, to build sensitive detectors, hoping to catch faint signals from WIMP particles, leading dark matter candidates in the silent depths of underground mines. This is a marvelous blend of human history and modern science, where ancient metal from the Roman Empire becomes a tool to touch cosmic secrets, moving us with unexpected time connections. Even a recent discovery suggests dark matter may leave fingerprints on light, tinting it faintly red or blue depending on type, a subtle trace next-generation telescopes could detect, opening doors to more direct observations. These advances not only enrich dark matter's story but ignite hope that one day we will better understand the 95% of the universe still in shadow, turning mysteries into inspiring tales. When you gaze at the night sky, you might see thousands of twinkling stars floating against a silent black backdrop. Those lights come from stars dozens, even hundreds of light-years away. Meaning each time you look, you peer into the past, seeing moments long before humans existed on Earth. Yet what you see, however beautiful, is only a tiny fragment of the immense picture we call the universe. Like viewing a shattered mirror piece, reflecting part of a vast entity while the rest remains forever out of sight. And a question echoes from the endless void: what about the parts our eyes can never reach? What awaits beyond that invisible curtain? The latest discoveries from the James Webb Space Telescope have revealed hundreds more ancient galaxies at the observable universe's edge, with light beginning its journey mere hundreds of millions of years after the Big Bang, providing sharper images of the universe's infancy, where first stars exploded and formed initial structures, amplifying our amazement at the richness hidden even in the small visible portion. People often say the universe is everything. But what does everything truly mean here? In scientific language, we distinguish between the observable universe and the actual universe. The observable universe is the portion where light has reached us since the Big Bang, 13.88 billion years ago. Based on light speed and space expansion, that range spans about 93 billion light-years. This number seems absurd since the universe is only 13.88 billion years old. How can it be 93 billion light-years wide? The reason is that while light travels, space itself expands, stretching distances between galaxies. Thus, what we see is not just light's journey but a picture of space inflated over time. As a result, our observable bubble is far larger than the universe's age. But pause to reflect. We call it the observable universe because it is all eyes, telescopes, and modern technology can access. Meaning beyond that boundary lies an infinite expanse where light has never had a chance to visit. It does not mean non-existence, we simply cannot see it. The latest models from Planck and James Webb data confirm the observable universe's diameter at 93 billion light-years, with higher precision, showing uneven expansion in different regions, hinting at even greater fluctuations beyond. If likening the universe to a vast ocean, what we hold is merely a droplet in our palm. This droplet sparkles beautifully, but it would be naive to think the ocean is only that much. This feeling recalls ancient times, when people stood on shores believing the horizon was the world's limit. They could not imagine continents beyond. Today we face a similar situation, except our horizon is not the line where sea meets sky but the cosmic horizon, where light is blocked, where space expands faster than light speed. Beyond that boundary, what exists may surpass even the boldest imagination. If we only see a small bubble, the natural question arises: how many other bubbles coexist outside? There could be gigantic galaxies, unignited stars, unborn civilizations, or even entirely different physical laws. Perhaps outside the observable bubble, space stretches infinitely like an endless field without fences or stops. Or it might divide into countless regions, each a world with unique conditions, like innumerable islands scattered on an endless ocean. And we, with the Milky Way, are just a dust speck on one of those islands. Recent studies from the DESI project have measured expansion more precisely, showing dark energy comprises about 68% of the universe, reinforcing ideas that space beyond could be infinite and more diverse. The fact we are confined to the observable bubble not only evokes humility but opens a door to imagination. Each time we observe distant galaxies, we touch the bubble's surface, like fingers on transparent glass separating us from a far vaster space. Strangely, the deeper we look into the universe, the more we realize what we know is a tiny part, and the unknown is exponentially larger. Perhaps this imperfection makes the exploration journey beautiful. For if we knew everything, the universe would cease being a mystery, and humanity would lose the drive to gaze skyward. Imagine if we could step beyond the observable boundary, what would we see? An infinite universe stretching on, or a colossal structure encompassing all? Perhaps countless other universes, each a bubble in a giant foam of reality. Maybe we would realize our believed all is just a layer in an endless multi-tiered network. And in that moment, the question shifts from how large the universe is to whether there is ever an end. Even more astonishing, within this 93 billion light-year limit, we have witnessed hundreds of billions of galaxies. Each galaxy holds hundreds of billions of stars, and many stars likely have orbiting planets like our Sun and Earth. The numbers are so vast that counting each star would never finish in a human lifetime. Yet all these wonders remain in a mere droplet. The ocean beyond we have never seen or touched, but it exists, expands, and invites us onward. Interestingly, calling this range the observable universe implicitly acknowledges another universe beyond sight. We know it is there, but cannot peer through. Like Plato's cave dwellers seeing only shadows on walls, never the true light outside. The question is whether humanity will ever escape the cosmic cave to see reality's primal light. And perhaps here we realize human knowledge's limits are not failure but opportunity. For each time we reach a boundary, we invent ways to surpass it, stronger telescopes, bolder equations, grander dreams. The observable bubble, instead of a prison wall, becomes a mirror reflecting humanity's eternal yearning to transcend itself. But before pondering distant unreachable regions, a special door exists right within this bubble. An invisible wall separating us from the universe's dawn. Where light was unborn, primordial darkness still guards secrets. And to proceed, we must pause there before the primal light wall. Data from the Euclid mission launched in 2023 is mapping billions of galaxies to better understand dark energy, potentially soon revealing more about this boundary. There is an intriguing yet limiting truth. We have never truly seen the universe at its birth moment. The closest science reaches is a hazy light curtain covering the sky like thick fog. Known as the cosmic microwave background, or CMB for short. It acts like a massive velvet curtain dropping just as the play begins, allowing the audience only faint backstage glimpses, never directly witnessing the stage's first illumination. To understand better, envision the early universe. Right after the Big Bang, everything compressed in an extremely hot, dense energy block. No atoms, no separate protons or neutrons. All dissolved in a radiant plasma sea where light was constantly absorbed and scattered. In that state, the universe was utterly opaque, like a boiling soup pot where no light ray could escape. Every photon, light particle, trapped in chaotic dance, colliding endlessly with free electrons, never traveling far. Time passed, the universe expanded, temperature dropped, and after about 380,000 years, a special moment occurred. Electrons and protons first combined into neutral hydrogen atoms. Then photons were freed, flying in all directions. And from that point, primordial light began its billion-year journey, reaching our eyes and telescopes today. The image we observe is not the universe being born but the universe just opening its eyes for the first time, as the opaque plasma curtain lifted. This carries deep meaning. We will never directly view the Big Bang instant. We only see the lingering afterglow, a faint snapshot from the distant past, CMB, considered the oldest echo, the universe's first group photo. When scientists map CMB, they find the sky filled with faint bright spots with temperature fluctuations differing by just 1 part in 100,000. Yet those tiny variations hold all seeds of today's universe. From first stars' formation to galaxies' birth and life's emergence. Latest CMB maps from the Atacama Cosmology Telescope reveal subtler anomalies, supporting inflation models and hinting at dark matter. Pausing to think, you realize this is an enchanting paradox. Everything from Earth to the Milky Way, galaxy clusters to superstructures, originates from tiny ripples in that CMB map. Meaning all reality with its richness and complexity was programmed from extremely subtle oscillations in the universe's infancy. CMB is like an old child's diary, where smudged pages reveal a lifetime's fate. Yet it also reminds us what we know is merely fragments of a larger story. For even with precise CMB measurements, we only see from 380,000 years after the Big Bang, not the initial instant. What happened in those 380,000 years? We know of cosmic inflation, ultra-rapid expansion phases, but all remain hypotheses. We stand before a wall, seeing faint light through, but never knowing what truly occurred on the other side. You might ask, if we cannot see through this light wall, how do we know what happened? The answer is indirect signs. Like hearing echoes in a valley, inferring cliff shapes, gorge width, even distance from sound. Scientists use CMB as an echo to deduce early moments. From its distribution, they infer matter density, dark matter ratio, even the universe's ultimate fate. But one truth chills many. The light you observe in the night sky comes not only from twinkling stars but also from CMB itself. If human eyes were sensitive enough, the sky would always glow faintly in microwaves. A pale light enveloping everywhere. In fact, when turning on an old analog television without signal, the flickering snow on screen is partly CMB. You are seeing Big Bang's remnant light. Light that traveled over 13 billion years to hit your living room antenna. In that instant, the universe becomes strangely intimate. No longer an abstract distant concept, but something touchable in daily life. Like viewing an ancient painting where faint strokes still hold billions of years' breath. Yet the more we understand CMB, the stricter our vision's limits appear. This light wall is the final boundary we cannot cross. Behind it, moments closer to the Big Bang lie forever beyond observation. This makes the truth-seeking journey both painful and glorious. Painful because some secrets are untouchable, glorious because from scant pieces we built a majestic picture. And perhaps this is limitation's beauty. If we saw everything clearly, the universe would lose its mystery. Because of the light wall, humans must imagine, infer, yearn. That curtain is an eternal challenge spurring human intellect forward. So when viewing CMB, we see not just past's faint light but our own reflection. Tiny beings lost in a gigantic universe yet carrying infinite desire to touch the impossible. Recent data from the South Pole Telescope have detected more inflation signals, reinforcing this picture. If our vision is blocked, we must find another path. And that path opens from a grand phenomenon, space's expansion. Not ordinary expansion but endless acceleration, a clue potentially leading to an infinite universe's secrets. One strange discovery cosmologists made after decades of observation and measurement: our universe seems perfectly flat. This term sounds simple but hides one of science history's most shocking findings, opening possibilities that the space we drift in may extend endlessly, without borders or ends. Saying the universe is flat does not mean it resembles a thin two-dimensional sheet. Actually, the universe still has three spatial dimensions, with depth, height, and width. But its geometry operates by flat rules, meaning parallel lines never meet. To visualize, imagine standing on a vast table. Draw two parallel straight lines on it. They remain equidistant forever, never intersecting no matter how far extended. That symbolizes flatness. Conversely, on a sphere like Earth's surface, initially parallel lines like meridians eventually meet at poles. So how do we know if the universe is flat or curved? Scientists found answers in the ancient universe map, the cosmic microwave background. By observing tiny fluctuations in CMB, they calculated primordial structures' opening angles. If the universe were curved, those angles would distort like viewing through convex or concave mirrors. But results are astonishing. Our universe is flat to near perfection, with error only about 0.1%. That number is not just a measurement but a bold statement. The universe may have no end. This implies an overwhelming meaning. A nearly flat universe is almost certainly one capable of infinite extension. If you pick any direction and fly straight forever, you would never return to the start like circling Earth, nor hit an edge. You simply continue onward endlessly. This notion is both beautiful and frightening to many. Like standing before a shoreless ocean, where you could sail eternally without seeing land. Yet the universe's flatness means more than geometry. It ties to a delicate balance hard to believe. For the universe to be flat today, total energy, matter density, radiation, and dark energy must reach an exact value. A slight deviation in millions, and the universe could curve, collapsing to a point early or expanding too fast for galaxies to form. In other words, the universe's flatness evokes a strange feeling as if an invisible hand finely tuned reality's basic parameters. From a human perspective, this presents a profound paradox. If the universe is truly infinite, anything possible will happen not once but countless times. Meaning somewhere in space far beyond sight, another version of you could exist. Living in an identical city but with one small decision different. In infinity, every possibility becomes reality, and you here are just one of countless versions of the same story. This thought overwhelms and trembles us, questioning self-uniqueness. If countless other me's exist, what meaning does this I hold? However, even imagining an infinite universe, we remain limited in our observable bubble. Flat universe does not mean we can reach everywhere, as distances are so vast light has not arrived. It is like standing in an endless field but seeing only a few kilometers around. Beyond that boundary, everything exists but forever out of sight. The infinity we speak of is thus both real and illusory, close yet distant. Meanwhile, flatness reveals other stories, sometimes beyond physics. Some see this strange balance as evidence of nature's fine calculation, as if the universe was tuned for life to emerge. Others view it as random among countless possibilities, and we simply inhabit a flat enough universe to exist and ask these questions. Either way, flatness is not a dry number but a door to philosophical musings on existence. To feel this, gaze at the night sky. Scattered stars, faint Milky Way streaks. All seem to drape a mysterious veil over you. But if the universe is truly flat and infinitely extending, behind every dark patch lie countless other worlds. Countless unseen stars. Thus, the night sky you see is merely a thin slice of a gigantic painting stretching endlessly. This feeling resembles standing on a beach, gazing at boundless water, knowing an ocean lies beyond imagination. But human eyes stop at the horizon. So what does the universe's flatness tell us? It whispers that space may be infinite, that what we see is just the tip of a colossal iceberg. It also reminds that in that infinity, our existence is both minuscule and wondrous. For a tiny deviation, and the universe would never allow life. We exist on a fragile tightrope in a universe flat to near absolute, like actors walking a thin bridge over an endless abyss. When we look up searching, another surprise awaits scientists. Amid seeming motionless flatness, strange motions appear. Galaxies not only recede but expansion accelerates over time. As if an invisible hand from outside stretches space, forcing everything apart faster than ever. That mysterious invisible power is called dark energy. A greater enigma than the flatness we just explored. Measurements from the Hubble constant in 2025 show the Hubble constant around 73 km per second per megaparsec, confirming accelerating expansion. In the seemingly calm flat cosmic picture obeying familiar laws, a mysterious current baffles scientists for decades. Galaxies, instead of moving purely by uniform expansion, seem pulled in one direction, as if an invisible river sweeps them along. This strange phenomenon is called the dark flow. When discussing galaxy motions, we usually think of post-Big Bang expansion, matter flung outward, continuing to recede today. That explains why farther galaxies recede faster, like ink dots on an inflating balloon. But if all were that simple, motions would follow uniform rules without bias. Yet when astronomers use space telescopes to measure, they find an anomaly. Hundreds, even thousands of massive galaxy clusters move in the same direction at terrifying speeds, about 2 million miles per hour. That speed astounds. But more frightening is the cause. Within the observable universe, no gravitational force is strong enough to explain this uniform pull. It is not from nearby superclusters or calculated dark matter density. In other words, galaxies are drawn by a power from beyond the cosmic horizon, where neither human eyes nor most advanced instruments can reach. This opens a shocking hypothesis. Perhaps beyond the observable universe lie structures colossal beyond imagination. Imagine a supercluster hundreds of times larger than anything known, lying outside our view. Its gravity could stretch even the space we inhabit. But another possibility, the pulling galaxies is not an object but a sign of a multiverse, where our space bubble is one of countless. When bubbles drift close, boundary suction or distortion could create the mysterious flow we observe. Pause to consider this. If dark flow truly originates from another universe, our observational limits are no longer the final barrier. We live not just in a gigantic universe but in a vast cosmic community, an immense ocean where each bubble is a sealed world with unique laws. And dark flow could be the thin thread connecting us to an unknown cosmic neighbor. Some scientists offer other explanations. Dark flow might result from random dark matter distribution fluctuations. Or it could be remnants of initial formation conditions, a scar still imprinted in space structure. But all hypotheses are pieces without convincing proof to affirm the dark in dark flow. Because dark refers not only to invisibility but to our knowledge's obscurity. The feeling when mentioning dark flow is like standing in a calm ocean, seeing surrounding boats suddenly tilt in unison while wind unchanged. You know an invisible force acts but cannot see it. You only sense through unusual shifts, through everything being swept away. And in the gap between known and unknown, human imagination ignites. If dark flow truly stems from a colossal structure or another universe pulling us, we are just dust swept by an endless river. The entire Milky Way with billions of stars and planets is a tiny element in a far grander motion. This truth makes us feel insignificant yet excites indescribably. For it proves the sky we gaze at nightly is only a small part of reality. Notably, dark flow is not a clear crack but a hint. A whisper from the universe's edge. It reminds that what we think complete still has gaps, that the full picture has unpainted dark areas. And sometimes those dark areas spur humans to explore endlessly, to question ceaselessly. After all, dark flow remains an unsolved mystery. But precisely because of that, it becomes a door leading beyond familiar limits. It encourages dreaming of greater possibilities, hidden worlds behind invisible veils. And perhaps one day that invisible flow will bring humanity closer to multiverse truth, parallel realities, unknown space regions. Yet mystery traces appear not only in galaxy motions, sometimes right in the ancient light picture the universe left. The cosmic microwave background, considered uniform backdrop, hides a strange scar, a colder region than the rest. That is the next clue, potentially a whisper from other universe bubbles. Latest analyses from Planck confirm the cold spot as the largest anomaly, with random probability under 1%. When humans first mapped the ancient universe via cosmic microwave background, many thought they would find only a smooth, uniform picture like a light fabric covering all directions. Indeed, CMB, legacy from the universe's early era, is largely strangely homogeneous. As if the entire universe woven from identical light threads. Yet hidden in that seemingly perfect fabric is a small crack, an unusually cold dark region like a scar on space's skin. Called the cold spot. This is not a simple dark patch or measurement error. It truly exists, standing out on the temperature map. While most CMB points fluctuate in tiny temperature differences, this cold region spans billions of light-years and is significantly cooler than surroundings. Like a large unexplained bruise on space's body. The question immediately arises, what created this scar? One hypothesis, the cold spot results from a gigantic void in the universe with unusually low galaxy density. When CMB light passes through that void, it stretches, loses energy, leaving a cooler imprint than elsewhere. Sounds reasonable, but detailed measurements show the void not large enough to explain the full anomaly. Like a puzzle piece not fitting, this hypothesis leaves doubts. A bolder explanation emerged, stirring human imagination. The cold spot could be a scar from a collision between two bubble universes. Imagine our universe as a bubble floating in a cosmic ocean. If another bubble drifts close and touches, the collision leaves ripples, an imprint. And that trace could remain in the ancient light picture we observe today. If true, the cold spot is the first evidence our universe is not alone, that it once touched another reality. This thought overwhelms and frightens. Overwhelms because it opens vistas that multiverse hypotheses are not mere theory but left clear observational traces. Frightens because it reminds bubble universes are not always absolutely separate. If collision occurred once, it could again. And a future collision might not just leave a scar but completely destroy our universe's structure. However, others argue the cold spot need not come from universe collision but could signal unknown physical properties. Some ideas suggest it relates to deeper space qualities, even hidden dimensions string theory mentions. If so, the cold spot is not just a scar but a slightly ajar door to reality's deeper layers. Facing the cold spot, we cannot help asking if it is random or a message the universe sends us. Viewing the CMB map is like seeing the universe's childhood portrait. And in that portrait is a strange mark. As if reminding the universe's past was not just a uniform explosion but held events beyond imagination. Pause and imagine, if the cold spot truly is a collision trace with another universe, we once touched a parallel reality. Perhaps on the scar's other side, another world formed with different stars, galaxies, even life. And our existence today might result from a gentle touch billions of years ago. A touch whose echo we see only as a cold streak in the sky. This leads to profound philosophical consequences. If universes can collide, their uniqueness vanishes. We no longer live in all reality but a small piece of an endless community. Like raindrops, each bubble universe can collide, merge, or leave marks on others. And the story we call our universe is just one drop in an eternal rain. Of course, no final conclusion on the cold spot yet. It remains an open mystery, a dark area in knowledge. But perhaps that uncertainty makes it a bright spot in cosmology research. The cold spot is like an unsolved question, always urging humans to look skyward and wonder if we are alone or part of a far larger picture. Viewing the cold spot, we hear the universe's whisper, saying what we know is just the beginning. Behind twinkling lights, behind near-absolute space flatness, remain unhealed scars, signs reality is far more complex and mysterious. To understand deeper, we need a grand theory, an idea once proposed to explain why the universe is flat, uniform, filled with strange traces. That is eternal inflation theory, where the universe not only inflates once but continues forever, creating countless parallel bubble realities. Recent models from BICEP and Keck array support inflation but have not detected primordial gravitational waves. If the cold scar on the ancient light picture suggests our universe is not isolated, eternal inflation theory takes this further to a level astounding even seasoned minds. Because instead of one universe born from the Big Bang, an endless process may exist, where space continuously births new universes like soap bubbles blooming in an unending cascade. To grasp this, return to cosmic inflation concept, the phase scientists believe occurred in the first instant after the Big Bang. In less than a trillionth of a second, space swelled at speeds exceeding light. This ultra-rapid expansion made the universe flat, uniform, explaining today's smooth CMB. But delving into inflation mechanics, physicists noticed something odd. Inflation seems not to end everywhere simultaneously. Imagine space as a vast energy field. In some regions, energy decays, expansion slows, matter and radiation form, birthing a universe like ours. But in others, energy persists, causing eternal swelling there. And in that endless swelling, new bubbles occasionally appear, separate universes, each with unique laws and conditions. This process is eternal inflation. It has no stop because while some bubbles cease expanding to become stable universes, surrounding space C continues inflating, allowing more bubbles. The result, instead of one universe, a bubble multiverse where universe count could be infinite. This thought fundamentally changes reality perception. If countless bubble universes exist, Laws we consider universal, from light speed to gravity, may apply only inside our bubble. In another bubble, physical constants differ, making atoms unstable, stars impossible, or time unimaginable. Some universes could be cold and empty where light never sparks, others richly alive with life forms beyond conception. And amid this vast vista, a more startling hypothesis: among infinite bubbles, some nearly identical to ours likely exist. If physical constants align similarly or event sequences repeat, somewhere another version of you sits in an identical world, hearing multiverse tales. And if infinity is real, not one but countless such copies coexist. Each with minor variations, a different decision, life path branch. This idea attracts yet challenges acceptance. It expands reality until all that exists blurs. The universe is no longer absolute but a piece in an endless tapestry. From this view, how the universe began loses weight, as each bubble is a chapter in an unwritten infinite book. However, eternal inflation is not fantasy. It builds on quantum field mathematics. Quantum inflation field decay models show it occurs unevenly, like boiling water bubbles. Each bubble forms in a specific space region, spreading while surroundings remain unboiled. Similarly, each universe bubble births from a localized region while the rest inflates eternally. In principle, this process never ends. If eternal inflation is true, an astonishing consequence: every possibility occurs somewhere. Every scenario, physical law variation, existence form all realized in some bubble. Our universe is one of countless possibilities, a sand grain in an infinite desert. Facing this vista, philosophical questions arise inevitably. If countless versions of you exist out there, where is the true self? If choices you thought unique are one of infinite variations, what is free will's meaning? And if life can arise in countless bubbles, what makes existence in this bubble special? Perhaps our ability to question this is this bubble universe's unique mark we call home. Though eternal inflation remains debated, it is one of cosmology's most compelling frameworks to explain anomalous observations. It also paints a reality picture grander than any ancient religion or philosophy imagined. The universe is no longer the sole stage but a forest of stages where countless plays perform simultaneously. And if many bubbles exist, the next question: are they completely separate or sometimes connected by invisible threads? Could events, mysterious phenomena we observe, actually be signs from other bubbles touching, like the cold scar in the sky? Perhaps despite vast separation, bubble universes whisper to each other through space-time fabric. Having grown accustomed to an endless multiverse idea where bubbles ceaselessly birth and fade, the next question emerges: are those bubbles entirely isolated, or do strange phenomena connect them like thin threads sewing a colossal space fabric? The answer, at least from bold scientific imagination, lies not only in inflation or microwave background but in hypotheses at physics and philosophy's edge. Start with white holes. If black holes are regions swallowing everything, even light, white holes are imagined opposites. They allow no matter in, only erupting energy out. In some general relativity mathematical models, black holes and white holes are two sides of the same coin, connected by a narrow spacetime channel. When matter falls into a black hole, on the other side a white hole might spew energy. Some scientists even hypothesize our universe's Big Bang could be a grand white hole eruption, result of matter falling into a black hole in another universe. If true, our origin's essence hides a thread linking universes. Another captivating phenomenon: cosmic strings. Imagine during universe birth in sudden expansion, space did not stretch evenly like smooth cloth but developed defects like water freezing into ice, sometimes leaving cracks. Those cracks in cosmology language are cosmic strings. One-dimensional ultra-thin but extremely heavy structures, a few kilometers long segment could weigh as much as Earth. Speculated if cosmic strings exist, they could bend surrounding space, create powerful gravitational lenses, even open connections between regions billions of light-years apart. Some bolder theories suggest cosmic strings could act as threads linking bubble universes, turning the multiverse from scattered collection to interwoven network. Then wormholes, science fiction's familiar symbol but seriously studied in physics. A wormhole imaginable as a tunnel connecting two spacetime points, allowing travel from one to another faster than light. Einstein's formulas permit wormholes, but stability conditions are extremely harsh, requiring exotic matter with negative energy to prevent collapse. Though never directly observed, wormholes are among most promising ideas for inter-universe communication. If a wormhole truly exists connecting two different bubbles, universe boundary concept blurs. Then the universe is no isolated island but a junction in a larger space-time network. But perhaps the strangest hypothesis is a mirror universe. Parallel to ours could exist a symmetric universe where time flows backward. While we advance to future, in the mirror universe events run reverse, from future to past. Some physicists suggest this not just imagination but could explain matter-antimatter imbalance in our current universe. If our universe has more matter than antimatter, the mirror could reverse, keeping overall multiverse balance. This visualization, beautiful mathematically, opens deep philosophical vista that every life, every moment in our universe has a reflection elsewhere. A copy running backward like a shadow on an invisible lake. Placing all these exotic phenomena together, white holes, cosmic strings, wormholes, mirror universes, we begin seeing a new picture. The universe no longer just vast flat space or lonely bubble in multiverse sea. Instead, a complex network where mysterious doors, threads, subtle symmetries connect seemingly isolated reality pieces. And in that vista, the question, do we live in a cosmic maze, where each turn is a portal to other realities we never knew we passed? These hypotheses' impact extends beyond pure science, forcing us to question human position in the whole. If Big Bang is just white hole eruption, our beginning not unique. If cosmic strings truly exist, what we call distance may be illusion. If wormholes can link universes, distance no longer limits. And if a mirror universe exists, time's flow we consider foundational is just one direction among countless possibilities. Pause to think. If one day humanity finds a way to open a wormhole or undeniable proof of mirror universe, all past, present, future concepts change forever. We would view the universe not as sealed room but corridor with countless doors, each opening to a separate world. These exotic hypotheses unproven, but their presence in science shows human imagination ceaselessly expands. From a small planet, we dare dream of space-time tunnels, invisible threads between universes, cosmic mirrors reflecting reverse realities. Perhaps those dreams, though unrealized, already define humanity. Beings forever yearning beyond limits, even when limits are the vast cosmos. And to continue this journey, we need a more powerful tool. For all those hypotheses, from wormholes to mirror universes, rest on a deeper foundation, reality's geometry and hidden spatial dimensions in structure. Models from LIGO gravitational wave detections support potential wormhole ideas. Imagine standing in a familiar room. 4 walls surround, floor below, ceiling above. Everything seems sufficient to describe our living space. But then someone tells you what senses perceive is only surface, tip of a colossal complex structure human brain struggles to envision. Behind 3-dimensional space we know could lie many other spatial dimensions, hidden, curled in tiny scales even strongest microscopes cannot see. That is string theory's idea, modern physics' most ambitious effort. According to string theory, all fundamental particles we know, electrons, photons, quarks, are not sizeless points as particle physics assumed but ultra-small vibrating strings. Like guitar strings producing different notes, these cosmic strings vibrate in multiple ways in multidimensional space, giving birth to particles with varying mass, charge, properties. If the universe truly builds from these vibrating strings, mathematics holds only if space dimensions expand to 10 or even 11. This idea challenges imagination. We are accustomed to 3 space dimensions plus 1 time. 1 dimension is line, 2 is plane, 3 is cube. But stepping to 4th, 5th, even 10th, mind's real. Yet mathematics unbound by intuition, string theory equations demand extra dimensions exist or the entire framework collapses. These additional space dimensions believed curled in extremely small sizes, perhaps 1/1,000,000,000 of a trillionth of a meter beyond current measurements. Imagine an ant crawling on electrical cable. To us, it moves along length, but to ant, cable has circular dimension around. Similarly, our universe may contain countless hidden subdimensions we simply cannot perceive. This not mere abstract math game but carries deep meaning on fundamental forces operation. We know 4 forces govern universe: gravity, electromagnetism, strong nuclear, weak nuclear. In current model, last 3 unify at extreme energies, but gravity remains separate, weaker by billions than electromagnetism. String theory suggests cause, gravity leaks into extra dimensions, while others confined to 3-dimensional space we sense. If true, multidimensional space existence explains observed universe operation. One bold consequence: in other bubble universes, extra dimensions could curl differently, creating entirely different physical laws. In our universe, like charges repel, in another, they might attract. In ours, time flows past to future. In another, time could reverse or loop. Even dark matter and energy's existence, today's greatest mysteries, could result from hidden geometry in subdimensions. This leads to classic philosophy and physics question. Are extra dimensions mere math products or truly existing somewhere? Physicists seek experimental evidence. Some Large Hadron Collider experiments hoped to produce extra dimension traces. For example, unexplained energy loss as if part leaked to another dimension. However, no direct evidence found yet. Still, 10 or 11-dimensional space idea remains compelling frameworks, providing basis to unify all physical laws in one picture. In science history, many once unrealistic concepts became pillars. Recall Einstein proposing space and time curve and expand, many called imagination. But relativity confirmed through countless observations. Perhaps multidimensional space awaits similar moment. When breakthrough discovery lifts mystery veil. If geometry is universe skeleton, energy is soul-blowing flow, making it not static structure but endless dance. And energy from tiny particle vibrations to space's grand expansion connects dimensions, forming vibrant whole we call universe. And perhaps in countless space dimensions hide doors to parallel universes where every possibility occurs. LHC upgrades in 2025 seek supersymmetry to support string theory. Pausing to reflect, multidimensional space concept not only changes physics understanding but touches deepest questions. Who are we in reality's infinite sea? Is human consciousness only in familiar 3 dimensions, or could it extend to invisible space layers? And if so, perhaps this curiosity, yearning to touch unimaginable, clearest proof we too part of multidimensional dance. If geometry frames and space dimensions weave universe fabric, energy is heartbeat, endless flow animating dry scene into living. And next question, is energy truly endless or bound by unpredictable limits? Energy opens exploration's next chapter. Thinking of void, we often envision completely empty space, nothing existing, no light, matter particles, sound, just silent deep pit. Yet in modern physics world, vacuum not absolute emptiness but invisible vibrant ocean, teeming with quantum fluctuations, virtual particles constantly appearing and vanishing in instants. The seeming empty expanse hides colossal energy trove if harnessable, enough to shake entire universe foundations. Vacuum energy concept from quantum mechanics, where Heisenberg uncertainty principle states no absolute static state. Even emptiest point always has tiny oscillations like calm sea still rippling. Those oscillations birth virtual particles, electrons, positrons, photons, flashing then fading. Meaning what we call nothing actually energy maximum region, foundation for all existence. But terrible paradox here. When quantum physicists calculate vacuum energy density via quantum field theory, number exceeds reality by dozens orders magnitude. Prediction: universe should tear apart from infinite energy from formation moment, not expand as observed. This vacuum catastrophe one of physics' greatest unsolved problems. Reality: universe expands stably, meaning mysterious balance keeps vacuum energy from unleashing potential destruction. Strangely, vacuum energy seen as prime dark energy candidate, accelerating universe expansion. If true, the empty foundation we thought actually decides entire universe fate. Tiny vacuum energy value change could create completely different universe. If larger by small fraction, universe expand too fast, galaxies never form. If smaller, gravity wins, collapsing everything to dense mass before life emerges. We exist because this universe's vacuum energy in narrow range unbelievably fine-tuned for life. In other bubble universes, vacuum energy like ours? Eternal inflation suggests each bubble universe own quantum vacuum constant, leading to vastly different realities. In one, vacuum energy too strong, space explodes chaos, no structure sustains. In another, too weak, all collapses eternal darkness. And perhaps only rare few universes vacuum energy just right, allowing stars, planets, life as we know. This point where modern physics meets philosophy. It forces question, our existence random choice among countless possibilities? Or deeper principle operating, forcing vacuum energy stable for life-bearing universe? Some call anthropic principle. Universe seems tuned for life. And since we here asking, this universe must have properties allowing it. Yet bolder explanations exist. One hypothesis, vacuum energy not invariant constant but changes over time or space regions. If true, reality fabric itself not absolutely stable but oscillates, shifts, opening possibility our universe one of countless continuously rewritten scripts. More extreme ideas, universe could undergo vacuum phase transition like water to ice or steam. In scenario, someday vacuum energy jumps lower state, destructive wave sweeping universe at light speed, altering all physical laws en route. If happens, life and known concepts vanish instantly, no warning. Chilling thought, but shows even eternal seeming foundation unexpectedly fragile. Yet another wonder, if vacuum energy can create or destroy universes, perhaps it caused first universe formation. Some theoretical models propose primordial vacuum quantum fluctuations sparked Big Bang starting all. Meaning what we call nothing actually everything, launchpad of existence. Broadly, imagine endless vacuum energy ocean where universe bubbles continuously form and vanish. Each bubble own quantum constant, own physical laws set, own history. Our universe one such bubble. Fortunate, stable long enough for life to emerge and self-recognize. You and I facing truth even quietest void brims power, must ask, what true existence foundation? Everything illusion floating from invisible energy ocean or vacuum energy ultimate reality nature a cosmic breath from which all begins and ends. While pondering vacuum mystery, another hypothesis opens stranger door. Perhaps black holes, dark abysses seeming to swallow all, actually birthplaces of new universes? And if so, our universe perhaps seed inside colossal black hole from another universe. Observations from Event Horizon Telescope on M87 and SGR are black holes confirm predicted structures. Viewing black holes, we often think absolute endpoints. Where familiar physics laws break, bottomless abysses, light cannot escape. But bold hypothesis reverses view, turning black holes from destruction symbols to birth gates. Perhaps instead of ends, black holes starts of new universes. Endless birth-death cycle. Idea stems from black hole information paradox, where scientists headache over fate of matter, energy, information falling in. Do they vanish forever or restructure somehow? Some physicists suggest when massive mass collapses infinitely, instead of crushing to absolute singularity, it rebounds in another space dimension. In that dimension, all energy releases like Big Bang, initiating entirely new universe. If true, each black hole in our universe pregnant with child universe, where physical laws may differ from ours. Imagine massive star collapse forming black hole. To us, star life cycle end. But in another space dimension, that moment new universe birth. Energy and matter sucked into black hole not lost but fuel for child universe Big Bang. Thus, death in this universe birth in another. If expanded, paints completely different cosmology picture. Gigantic family tree where universes successively birth via black hole mechanism. Our universe child of mother universe, and within ours, billions black holes nurture other child universes. In picture, No absolute start or end, only endless succession like Eastern philosophy life-death cycle. Concept also suggests interesting thought. If each child universe inherits part mother characteristics, perhaps cosmic natural selection form. Universes with physical laws allowing many black holes birth more children, over time dominating. Hypothesis physicist Lee Smolin called cosmological natural selection via black holes. From view, our many black hole universe not random but evolution cosmology result over billions years. Of course, all still hypothesis range, but opens fascinating philosophy doors. If universes reproduce, does universe start question still meaningful? Or actually no absolute beginning, only endless flow worlds nested in worlds like endless Russian dolls? In case, Big Bang we call all origin perhaps small event in endless cosmic symphony. Another vista worth pondering. If enter black hole, could see child universe birth? May forever beyond human ability, black hole no return point. But imagination, plunging dark gate then sudden bright, absolute darkness transforms light explosion, opening unprecedented space. There, physics operate differently, perhaps no time is known. If our universe truly another universe child, also raises if mother-child universe link? Or completely separate, never touch like parallel rivers in multidimensional space? Some hypotheses, child universe physical constants influenced by mother like biological inheritance. Others believe each universe completely new start unique laws. Philosophically, idea offers strange comfort. If star death births new universe, perhaps death always rebirth. Our beautiful life-filled universe result grand death in another world. And when this universe ends, leaves seeds countless new universes. Moreover, worldview makes rethink end nature. Perhaps no end points, only transformation one form to another. Black holes instead light graves become universe wombs. And cycle continues beyond human grasp but always ignites unending curiosity. So if black holes birth whole universes, colossal structures within our universe secretly control galaxy motions. One greatest mysteries invisible puller presence. What scientists call great attractor, where even our Milky Way pulled toward. Gazing skyward, Milky Way appears peaceful bright band stretching endlessly, seemingly still in vast space. But truth entirely different. Our galaxy,